I think everybody's here for this group right now. So come on in so you can get out of the sun if you like. So we have 3 different demos here at this tent that we're going to talk about. My name is Amy Apon. I'm a professor of computer science here at Clemson. I'm also the chair of the computer science division. And I've been working with Ronnie Chowdhury now for a couple of 3 years on different aspects of data analytics and intelligent transportation systems. And it's really a great collaboration because there's a lot of computing that's required in order to build an ITS. And so I bring expertise with my students in different kinds of computing systems and computing analytics approaches. So what I'm going to show you today is on the screen. I'm going to explain it first. So imagine an ITS system where you have all kinds of data devices. You have vehicles that are transmitting data, you have roadside units, you have people with cell phones, you have maybe social media that's creating information, and you would like to process that information from different kinds of services. So you have, and what you don't want to do, let's say you have millions of vehicles and roadside units, what you don't want to do is have each of those vehicles connect directly to every service, because then when you add another service, they'll have to connect to the new service. And if one of them fails or gets relocated, then you have to undo those connections, and that's a lot of work underneath. And so the typical distributed systems architecture for doing this is called a broker system. You put a software broker in the middle, and you have all the producers produce data to the software broker, and then the consumers will consume the data that they need from the broker and then do their analytics on it. So our task in this demo was to come up with a software broker system that would scale to millions of cars and maybe tens of millions of people with devices and things. And so that was one problem. The other problem is that right now the system that Dr. Chowdhury has set up in his lab is working on a single whole computer in his lab environment on a building on campus. And it works great for what they've got set up right now, but it's not very accessible to researchers at, say, Benedict College or across the state. And also, it's not very fault tolerant. If the electricity goes off in that room, then you can't get to that computer, and that broker system no longer works. So we wanted to come up with a system that would behave the right way as if it were a production system, that would have fault tolerance, be highly available, that would scale to a very, very large number, and then of course some business concerns like does it cost too much and things like that. So what we did is look at a solution inside the commercial cloud, because the commercial cloud offers those kinds of capabilities. Now, there are several commercial clouds out there that we could consider. One is Amazon Web Services, AWS. Another one is Azure. Google Cloud Platform is another one, and then there's some smaller ones out there. So we chose Amazon Web Services. We have a lot of experience in that, and also it's the largest cloud provider right now by far. But what we did could conceivably be done on a different commercial cloud service. So we're going to get hardware and a physical environment that we will rent on Amazon Web Services. And now we have to install an appropriate software broker, and we still have some choices. So one choice we could make is to use an open source software called Kafka, which you can download from the internet, you can install it on your computer, and you can use it. And then we wanted to compare that to a managed service that Amazon provides called Kinesis. And they have some trade-offs. They have slightly different features in terms of the number of simultaneous streams that they can support on a single whole computer. On Kafka, it'll support a certain number on a whole computer, and then when you exceed that number, then you have to add another whole computer. And so there's a step function there in terms of price. Whereas with Kinesis, you can add different streams, and the jump is just you add a single stream. And they have different also characteristics in terms of how long they hold the messages, whether or not they guarantee the message to be delivered, other kinds of availability. Kinesis can scale to a very large number. We're not actually sure that Kafka can, although it probably can to at least a reasonably large number. So what I'm going to show you here is the infrastructure that we built using Kinesis. Now this is actually a really tiny demo, but what it does is it will accept producers, any number of producers really, producing into the broker, and the broker is itself sort of invisible to you. It's running in the cloud and you can't see it. And then the consumer will consume that information, and then it can do whatever it wants. It can perform some analytics on it. So the messages that we're simulating in this case were inspired by some data that we had access to from a partnership with BMW. And what they were looking at were security messages, network security messages that were coming off of vehicles. Well, we couldn't actually use those network security messages. They're proprietary to BMW. So what we've done is create a fake data stream, a synthetic data stream that has the same characteristics as these security messages. The messages are the same length and they come in at the same rate. And the analytics task here is to find the bad guy. If you see a message that comes in that looks suspicious, then we want to flag it and say that's a bad guy that sent that message. And so on the right here, this was actually a video that was recorded yesterday because we don't quite have the network connectivity that we want here. But this was the demo that we actually ran in the lab yesterday. So we've got 3 different producers that are producing messages, and they're producing them into the Kinesis broker that's executing in the AWS cloud. And then the consumer is extracting those messages from Kinesis and then potentially doing some kind of analytics task on them. So the things that we have tested on Kinesis are how long does it take the message to go through Kinesis, because we want it to be really fast, and how quickly will it scale. If we see a sudden burst of messages, will it scale quickly? If you have a lot of cars, say at the end of a football game, and all of a sudden there's a lot more traffic than there was 6 hours ago, will that broker scale to handle all those different messages that we have now? And then we also looked at cost concerns to make sure that we're proposing a system that could potentially have business value for all the different servers that are out there. So that's the demo. That's what we've done. And now let me see if you have any questions. Oh, and let me actually introduce Zhong Lin is the graduate student that built the producer and the consumer, and also helped code up the Kinesis and the Kafka brokers.
Yeah, maybe one quick question.
Sure.
Now, again, my background is not computer science. I'm a civil engineer.
Okay.
But the broker that you are referring to, is it a one broker or brokers in parallel?
It's a lot of different tasks that work in collaboration with each other. So it's not a single task or single program or single computer, because then we'd have a single point of failure. Mm-hmm. So it's a collection of tasks that work on a collection of computers depending on the load. Okay, but always at least 2. Okay.
So what about big communication providers like AT&T, Verizon, or any of these services available?
So the network services are available, but the service that manages this data stream, these messages, they're not available directly from AT&T. You have to build that over the networking infrastructure. Okay, so think of the network as just the pipe. And now I want to put something in the pipe that will pass the messages through, something that I can process.
Amy, what's the latency for going from through the broker?
Actually, so might know the answer to that.
Yes, it's a rate of 10 million record per hour, and the average latency between the west coast to the east coast and to the west coast is about 2 or 3 seconds to access.
Most of that's the speed of light. The speed of light is not nearly as fast as you want it to be.
Yeah. And the whole data
But the latency through the actual brokers is really fast. It's what, milliseconds?
Yes.
A very small number of milliseconds.
So I see some contraptions behind it.
That's a different demo. So we have 3 demos. That's just the first one.
So I'm seeing some crazy signs there. One of the messages is, I want my nose in red or something.
Yeah, so again, this is fake data that we generated.
Trump created it.
Zhong created the data to have the same structural characteristics as the BMW data that we have. So the data itself is
So where's the bad message in there?
have you found the bad message yet?
This is a program in Linux. Yeah, very popular called Fortune.
It's a hunting exercise to find the bad message. So one question that I was asked by the last group had to do with open source versus managed service. So Kafka is an open source software, and open source is typically free. You download it from the internet, you install it, and it doesn't cost anything. Except free software is kind of like free puppy. So you have to feed it, you have to water it, you have to do its upgrades, you have to clean up its mess, and you have to pay experts that know how to manage that free software. So it's not really free because you have to do all these things with it. A managed service from AWS we'll do all of those things for you. We'll do the upgrades and installation, and we'll manage the scalability and many of those other things. So it costs a bit more, but then the expertise required to maintain that middleware is much lower than the expertise required to maintain an open source system. So that's one of the trade-offs that we're going to describe in the paper that we write.
So in mid-2016, Greenville County was identified as one of 10 cities in America, an Envision America city.
Okay.
And Amazon Web Service offered us free access to their service. And our procurement people said you can't use it in Greenville County.
Oh.
Greenville County system, because it's a service that's provided that you could buy, so you have to go through an RFP process to select that. How do you get around that?
Okay, so these are state purchasing constraints. It has really nothing to do with whether the technology is useful or not. So we're getting some help from our university's IT folks to go through a bid process on our behalf. So Amazon, not Amazon directly, but one of their third-party providers, actually several of their third-party providers, they went through a bid process on cloud services. And it's sort of a pre-bid process. They went through a long, convoluted bid process to be able to select a provider for cloud services. And what it does is once you go through that in a competitive way, then you've done the bid.
So could Greenville County use your research and your expertise and say, we want to piggyback on
We
what
could.
Clemson
We
University
could.
does?
So they can't use the contract directly because that's already completed. But you could go through the same process that we did.
And just say, we know this is a successful bidder and we want to do what Clemson did.
Well, you might have to do the bid process, but you could at least use our mechanisms and like bid documents and things like that. Yeah. But you're right. That is a constraint that you have to deal with at the state level when you want to do production kinds of services. Now, for small research projects, all the cloud providers will give you credit, what they call credits, for free, and that's how we're doing this. We have free credits, and the project can do small-scale experimentation without it actually costing you much. And there's also a certain amount that you can buy that's under the bid threshold. If you buy, I forget, it's 20,000 or 25,000 of cloud services that you can buy per year. As long as you stay under that threshold, then you don't have to go out for bid. But you're right; it's a concern as you scale up.
I didn't mean to jump a bad.
No, it's a concern as you start to scale up. Well, I'm going to go to the second demo then. So the second demo is Late Nizam.
So it's very hard to hold this poster because of the. So here we are showing some devices, high-quality devices. I think already you see some devices there, right? So exactly same devices we are showing here. So this is onboard unit, like using this device, using dedicated short-range communication, you can connect with the roadside unit. So this is the roadside unit. So this is from one company, that is Coda Wireless, and this is a different vendor, different company. This is other system. So we have devices from two different companies. So this is the same thing, like this is also a onboard unit. In the vehicle you can put it, and that vehicle can be connected with the roadside unit. So roadside unit can collect data from the vehicle and process it here. And also this roadside unit will be connected with the server system. So if you look at this figure, you can see this is the connected Clemson University connected vehicle test bed. So this is the perimeter road. I think Dr. Chaudhary mentioned about that. So this is a smart road for us. And we have fixed edge, so like this device at 3 different locations. And it has a range like 1,000 feet. So it could be up to 1 mile, but it depends on the environment. So we put all those this kind of devices at three different locations, such that like it can overlap. So they can communicate between each other, and also they can communicate with the system node that is called a server, or you can call it cloud. So so we are calling each vehicle mobile edge, that is mobile node. So it is a edge-centric cyber physical system. Whole system you can call it edge-centric cyber physical system. So at the lower level we have mobile edge, and at the next level we have fixed edge, that is fixed at the roadside, and at the higher level we have system node. But you can have more layer. So it depends on your requirement. For example, now we have roadside unit, and cloud, right? So you can add more layers, just like regional service, and maybe at a step level. So you can add more layers and you can connect with each other. So this is our test bed, guided vehicle test bed, and these are the devices we are using right now. And this is onboard device, like you can collect fuel consumption and other vehicle related data using this thing. So right now we are getting vehicle ID, vehicle location, speed information. So all those things we are getting, and we are developing application based on that. And another thing, we have three different road traffic signals on this corridor. So we are developing applications based on traffic signals. How we can make it more eco-friendly, less fuel consumption. So this is what we are working on right now. And if you have any question about devices or about testbed, yeah.
So you mentioned sustainability or eco-friendly.
Right.
And so the concern, or from the environmental engineering point of view, do you have the capability of looking at driver behavior and then looking at emissions based on that?
Not exactly driver behavior. For example, I can give you an example. So let's say you have three different signals and you are traveling through this road, right? So you may hit red signal, right? So we can develop, we are working on it, we are developing an algorithm that can adjust the speed such a way you can go through this signal with minimum fuel consumption. If you have the minimum fuel consumption, you will have less emissions. So this is how it is connected. But there are some other applications too. For example, instead of just developing application for each vehicle, you can do a platoon of vehicles, and they all will be connected, and they will follow the leader vehicle, and this way it will save the fuel consumption.
And one thing I just want to mention is one of the projects that's going to come out this year, the C2M2 projects, is that we are going to have video analytics to identify vehicles as they come through. So using the GPS signal from here, we can identify approximately where it is. We can pinpoint the two, so as we get instrumentation information back from the vehicle, we can identify it as well. And in video, we can also track the vehicle as it moves between lanes and things like that. And so that's the other thing we're trying to do, is feedback and say, okay, you know, we can actually talk back to the vehicle, or you know, record that information, identify those vehicles that are driving erratically. So combining all the various technologies gives, you know, it's game on.
So let me just add something about Mizan's architecture here. If you have a decision that has to be made in a very short period of time about the car itself, then you might put the computer in the car, and the message actually never leaves the car. But if you have a message, a decision, let's say a queue warning, where it's, you know, it's in my region but it's outside my car, then you might need to send data from multiple cars to the roadside unit, and you could put some kind of processor on the roadside unit to make the decision there. And it doesn't have to go to the cloud, although you may eventually send that information to the cloud. If you have another kind of decision that you need to make over a few seconds, and it requires a broader geographic set of information, say a trip plan, then you would want to send that information from the car to the roadside unit, or maybe directly from the car all the way back to the cloud, and let the cloud analytics engine make the decision and send the response back to the vehicle. And so we can have multiple tiers of processing depending on the time and the geographic nature of the data, the time required to meet the request, and the geographic nature of the data.
Yes, that could be also also needed when we have a high level of implementation percentages, right? So many people are benefiting this one.
That's true. I mean, this cloud can be vendor agnostic. You can, you know, if you just prescribe, if you tell them what the message format's supposed to look like, then you could design a cell phone app that would send messages to the cloud, like Waze, for example.
So in terms of deployment, the roadside equipment, How do you know install them? Are they going to be box or
Yes. Yes, it is in the box. So we are using a box that is like that will have the weather protection and any kind of protection. So we deployed in that way. And also we have a devices with this roadside unit that is called roadside device, and that is a small computer. So there I think there is a laptop is acting as a roadside device. So you can add any processing unit with this roadside unit because it has a limitation in terms of computational power. But you can add a device. So here we have that device, and at the same time that's why we are calling it fixed edge, not exactly the roadside unit, right? So we are calling it fixed edge because it has roadside unit, and at the same time it has a small device that has higher computational power. So you can do the computation at this location too.
What about the cyber detection that they illustrated in this one down the hill?
So there, how we develop the architecture for the cyber attack. So you can run some algorithm here at the roadside unit and at the cloud level. So we are running at the both levels. So at the system level, you can look at it, and you can also look at it like for a roadside segment. So right now, what he is running for, he's running at roadside unit and detecting any kind of attack in this like DSRC communication range. But he can deploy it at the cloud level too.
And one more, right?
So,
All right. Hi, everyone. I'm Charles. I'm from Dr. John Wagner's group in mechanical engineering here at Clemson University. So the research I'm conducting is because in real life when we're driving on a road, sometimes we tend to play with our phones a little bit. Like that causes deviation from the lane, and that can cause accidents. So what the research I'm doing here is an exploration of the lane keeping control for the vehicle. So the lane keeping controller that I'm using is a feed-forward feedback controller in combination with the fuzzy logic. And this controller can also applies to lane changing events as well. And we also have a steering device here. It's called Event Falcon. This steering device is a 6 degree of freedom device that is a USB based. So it's really mobile, and when it's in the car, it does no harm to you when the car hits something. But typically when the steering wheel, when a vehicle hits something, the steering wheel will shoot an airbag to you and it causes some damage to you. But this will not cause that kind of damage. So I'm going to here do a demo of what's it like driving on a roadway.
That's how we are. When you really need them, they go to sleep.
Yeah.
Everything.
I can use this piece. So I'm gonna run this. The software's kind of slow. Excuse me, the device is not communicating really well.
There it is.
Oh. All right, so the simulation started. As you can see, I'm barely touching this. I'm actually driving on a road, and it automatically provides feedback to me and try to keep on the center of the lane. I'm barely giving it any force. As you can see, yeah, it's a sort of
Are we seeing the back or the front of the car?
we're in the back.
Back of the car.
Yes. So this means that we don't need to, when we're driving the vehicle, we don't need to give any efforts to the steering wheel or steering device. We can just, hold it. Just look at the front of the road. If there's anything emergency happen, we can get involved. But if it's not, the vehicle just drive itself.
So that device controls the steering of the vehicle?
Yes. That device controls the steering.
Based on
Like control algorithm of the lanes.
Are they
Based
markings?
based on the lateral error and the heading error of the vehicle.
also the GPS? Or
Yeah.
something like that?
And that's because so the simulation is calculating the distance between the center of the vehicle to the center of the road. That's the lateral error. And also it's calculating the heading error of the vehicle. So when a vehicle is just trying to compensate, so the vehicle will compensate the curvature of the road when it's trying to go to a certain location.
Have you tested in an actual vehicle?
I haven't. That's the next step I'm going to do. That's the first step of the research.
Sight distance.
It's lateral error.
It's not considering any of that. It's only knows its position, right? It's only
Yes.
knows its position.
Its
So
position
it's not,
is-
this particular thing is not considering any of the vehicles too, right? So it's only considering its position relative to the center line that's mapped. And so, yeah, and so we'll assume that the GPS is accurate, which in real time with differential correction will be really accurate. So that's pretty cool though. Okay, I want
So it means that it has to have a very strong machine learning capabilities in case of maintenance or change of.
Well, this is not based on machine learning. This is based on control algorithms.
Okay.
Feed-forward, feedback control algorithms.
Yeah, so this is spontaneous reading of where it's located.
This is spontaneous reading of where the vehicle is right now and apply a control force to it.
Does it pay attention to the speed limit? Sorry? Does it pay attention to the speed limit? Speed limits and does not.
it's just doing the one thing, but combined with other systems, then
Yeah.
you can control it.
Yeah.
So it's just one. It's one in many systems.
This is the study of lateral dynamics, so it's not considering the longitudinal speed.
So in essence, it will minimize the runoff of the accident runoff from the road.
Yes, so if you run off from the road, it will immediately give you a feedback to pull you back.
Is this off the shelf?
That is. It's off.
The software is
Software in a simulate. MATLAB simulate.
MATLAB simulator, yes. And which tool are you guys using? You said forward or
Feed forward, feedback,
Okay.
fuzzy logic.
Fuzzy logic,
control,
okay.
yes.
Did you, I'm sorry. Did you say that the algorithm would understand the difference between running off the road and like a purposeful lane change?
No, that's two different events I'm studying.
Oh,
Two
okay.
separate. It won't understand that.
Okay.
Okay, that's
That's two different events I'm trying to study. One is lane change and one is lane keeping. It's
Okay.
two different studies.
Thank you.
So, but I guess in the real life you might.
Maybe when you turn on the turning light, the turning signal,
Yeah.
then that would maybe switch from one to the other.
Yes, exactly.
Okay.
But it's definitely that's definitely a really good question because in real life sometimes you do want to do a lane change, and the system will try to pull you back.
Has happened to me with the vehicle that we have has the lane keeping assistance, so I try to keep in the lane. So I look my rear view mirror, there wasn't any vehicle, so I didn't turn on the turning signal. So I go to change lane and the car shifts me back in the lane. I say, oh my God, what just happened? And then I realized it was that, so I have to turn on the light and then change lane and then
Turn it on.
carry on, yeah. There is the option of turning on and off.
There should be.